Okay, so when you start drawing Lewis structures, you may run into a situation where it's possible to draw multiple different structures for the same formula. So if you have the option of selecting, one of multiple plausible Lewis structures, we need to figure out a way that will tell us what the correct one is. And the thing that we use to help us determine what the most plausible Lewis structure is we use something called a formal charge on the atoms and for the molecule of the species as a whole. The formal charge can be defined as the difference between the number of valence electrons and the associated electrons in that particular scenario. The difference here again is important. So we need to know the valence electrons that we have that we're working with for that particular element, and then the associated electrons. So what exactly is the associated electrons? These are all of that atom's lone pairs or non-bonding electrons, but non-bonding are the same as lone pairs. So a lone pair would have two non-bonding electrons. And then we also consider half of the atom's bonding electrons. So for example, in a bond, in a single bond, okay, that's a line, single line, there are two electrons. So half of that would be associated with that atom. Okay, so two electrons involved. So half of two would mean one electron to be considered in this calculation. All right, and we'll sum these together. We'll stick them in here, and then we'll do a simple subtraction to figure out the formal charge. So let's take a look at an example of calculating the formal charges on atoms in a Lewis structure. This is the Lewis structure for a molecule known as ozone, O3, which is an allotrope of oxygen. We saw this in the earlier sections, actually. So one plausible Lewis structure for ozone is as follows. So ozone is O3. Okay. So we have all three oxygens connected to each other. The oxygen on the left has a lone pair to the oxygen in the middle. Oxygen in the middle has a lone pair on it, one lone pair. Oxygen on the right has three lone pairs on it. So if I take a look at the oxygen on the left and I calculate its formal charge, okay, so the formal charge for this one would be equal to the valence electron. So valence electrons for oxygen is 6. You get that from the periodic table, minus, right? So we go back to our formula here, the valence electrons minus the associated electrons. So the associated electrons are the ones, the lone pairs, so 2 plus 2, that's 4. And in a double bond, right, remember 4 electrons are shared in a double bond, we take half of those. So 4 electrons divided by 2, that would give 2 associated electrons. Plus the 2 here and the 2 there, that would give a total of 6 associated electrons. 6 minus 6 would give 0 for the formal charge on that oxygen. If I take a look at the oxygen in the middle, so this one here, I have a lone pair, I have a double bond, and then a single bond on this side. So the formal charge for that one then would be, and following the same thing, our valence electrons for oxygen, which is 6, minus the associated electrons. So we have a lone pair. This counts as 2. And how many bonds are on it? We have a double bond, right? That's 4 electrons, and a single bond. Those are 6 electrons total that are being shared. Around that O, we take half of those. So that's 3, plus the lone pair 2, that's 5. So 6 minus 5 then give us formal charge of +1 on that oxygen in the middle. And then the oxygen on the right side, this one here, we have 3 lone pairs and then 1 bonding pair of electrons. So the formal charge for that one, again, will be the valence electrons, which is always 6 for oxygen, minus the associated electrons. We have 2, 4, 6. Okay, so that's 6 electrons total for the lone pairs, plus 2 electrons shared. We take half of those. That gives 1, say 6 plus 1 would be 7. So then our valence electron 6 minus 7 would be -1 to be the formal charge on this oxygen there on the right side. So Yes, it does involve a little bit of math, but you want to make sure that you use it to determine the formal charge because you have competing Lewis structures. We want to use a formal charge to help us break that tie. And what is going to allow us to break the tie? Well, when we have more than one possible Lewis structure, the best arrangement that we're going to choose is going to be determined by the following. You want to choose the Lewis structure in where all the formal charges are zero. Okay, so ideally, we want the structure where all formal charges are zero. That's preferred. If that's not the case, and we have to have formal charges, we would prefer to have small formal charges versus large ones. So for example, +1 or -1 versus, +3 or, -2, right? This is preferred. Lower, smaller charges are preferred. And the third thing here is that if you do have to have formal charges, they need to be consistent with electronegativities. That means that if you have negative formal charges, they should go on the electronegative element. On the most electronegative elements. Okay, so it needs to match up with those electronegativities. And again, these last two criteria here are only if there must be formal charges. So only if formal charges are unavoidable. You want to have small formal charges. We want the negative charges to be on the most electronegative elements. Okay, so if we take a look at an example, let's do a different one. Go back up. So here we have an example of a situation where we're given the formula for molecule of formaldehyde, CH2O, which you probably have heard about being used to preserve biological specimens. We can draw two competing Lewis structures for formaldehyde. We can have a situation where we have a hydrogen connected to a carbon, double bond to an O, and then an H. That is a plausible Lewis structure. We also have another instance where you have a carbon double bonded to an O, and then two H's on either side of the carbon. Okay, so which of these would be preferred? Because in both of these cases, right, everything has an octet that needs an octet. We've accounted for all of the electrons, all the valence electrons in both of these. So these are plausible. If we compute the formal charges, we can do it for each of these. So for the hydrogen here, the formal charge of the valence electrons 1 minus its associated electrons. There aren't any lone pairs. All we have is a bonding pair of electrons. So 2 electrons. We take half of that. So 1 minus 1 gives 0. Right? So we want formal charges to be 0 where applicable. That's going to be the same case with this hydrogen here on the right side. Right? That's also the same situation. Formal charge is also 0. If you look at the carbon here, the formal charge then would be the valence electrons of carbon, which is 4, minus the associated electrons. So we have the 2 that belong to the C, plus half of these 6 shared electrons. Okay, so we have 2 plus half of the 6 shared electrons. Half of 6 is 3, plus 2 is 5. So 4 minus 5 would give, it's in 1. That's for the carbon. If I look at the oxygen, okay, the formal charge there is the valence electron 6 minus the associated electrons for the oxygen, sorry. So we have the 2 that belong to it, plus half of the shared electrons. So we have 6 shared electrons around that oxygen. So 2 plus 3 would give 5. Click on it here, 6 minus 5 gives +1 for the formal charge on the O. Now, the hydrogens have formal charges of zeros. You have a formal charge of +1 on the carbon. You have a formal charge of -1 on the O. So that's compared to the formal charges on the neighboring structure. So again, the hydrogen, as you can imagine, formal charges there are 0 because they are just same as the example on the left side. Okay, if you look at the oxygen up here, Okay, we have formal charge, valence electron 6 minus the number of associated electrons. So we have 2 plus 2, so that's 4 electrons. All right, plus half of the shared electrons. We have 4 electrons that are being shared. So half of 4 would be 2. That would give 6 total. Valence electron 6 minus 6 gives 0. So that's oxygen. For the carbon, right, valence electrons 4 minus the associated electrons. We don't have any lone pairs on the C, but we do have 2, 4, 6, 8 shared electrons. Half of 8 is 4, so 4 minus 4 gives 0. So in this case, all of my formal charges are 0 versus having formal charges on the left. This would be my preferred Lewis structure. Okay, so where you have competing Lewis structures, you want to go in order, select the one where all the formal charges are 0, or if they have to be formal charges, you want lowest formal charges where possible, and you want those formal charges to be consistent with the electronegativities. Okay, so another phenomenon that you will encounter with Lewis structures is it may be possible where the single molecule cannot be represented accurately by only one Lewis structure. So this is different than having competing Lewis structures where you use formal charges to decide what's the correct one. Here we can actually have multiple structures that represent the molecule. So the thing about this phenomenon is we refer to it as resonance, the resonance structure. And what the resonance structure is just a hybrid of those possible, or those Lewis structures. Your resonance structures, right? These are things that we make up, and people looking at the formulas and the structures, they differ only from each other, or they differ from each other only by the positions of their electrons. Okay, and let's do a different example here on the right side. Let's look at the mole or the ion nitrate. So NO3 with a minus charge, right? We see that in the polyatomic list. It's a nitrate ion. We'll go through and draw Lewis structures, right? So we do our valence electrons. We have 1 nitrogen, we have 3 oxygens. Nitrogen is in group 5, oxygen is in group 6. So 5 plus 18, that's 23. And now I have a -1 charge, so we add that to our count. So 24 valence electrons in my structure. Okay. I put the least electronegative element in the middle, which is nitrogen, and then I have my oxygens all around. I'm going to connect them with a bond to begin with, and then I make the peripheral, the outer oxygens happy. They each have 2 electrons right now. They are all going to need 6 more in the form of 3 lone pairs on the O's. Okay, so that would give then in my structure a total of 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Those are my 24 valence electrons. I cannot add any more electrons in. Okay, so this has -1 charge. What you will notice though is that even though my oxygens are happy, my nitrogen is not, right? It only got 6 electrons around it. It needs 2 more. When your central atom is electron deficient, we can now move a pair of electrons in to make a double bond between the O and the N. Okay, so that is a plausible Lewis structure for the nitrate ion. Well, you may be thinking to yourself, why did I choose to move that pair of electrons? Could I not have moved the pair of electrons from the O on the left or from a pair of electrons from the O on the top? And the answer is, I sure could have. And when I do that, I end up with now resonance structure. So now, if I have my base structure I had before that I drew, with my negative charge, I could have moved this pair of electrons from the top and made a double bond on top of the N, and that would be acceptable. Okay, I could also have moved a pair of electrons from the O on the left to make the double bond on the left side. That's just I move a pair of electrons here. I can make the double bond on my left. And these are all resonance contributors to the actual overall structure of the nitrate. So you will notice that the only difference between these three structures is the position of the electrons, specifically the position of the extra bonding pair of electrons. So here it's on the right side, it can be on the top, it can be on the left. So where is it in reality? Well, the truth is, it's kind of spread across all of those positions, but any one of these could be correct for the structure of the nitrate. So these are all resonance structures. And again, the true structure is a hybrid between all of these. And this is the nitrate. And we represent resonance structures, the differences between them by using this double-headed arrow. You know, I drew mine from top to bottom. You could have drawn yours left to right, like it shows here for the carbonate ion, which is CO3 2 minus. So you have something similar happening in this example. Okay, so resonance is another phenomenon that you will encounter, and you will talk a lot about resonance if you ever go on to organic chemistry. That's a big deal in organic.